For this lesson, we're going to be looking at linear relations and comparing them to nonlinear relations. So our main goals are to identify a relation as linear or nonlinear given a graph or equation, and to identify if a relation is linear from a table of values by calculating the first differences. So let's start with our graph. This one can be the easiest to recognize. So if I look here, I have an example of a linear graph on the left-hand side. And if we look here, it's a nice line. It's a perfectly straight line. In this case, it's a positive line going up to the right. And if I look at this line, it's perfectly straight, and that's because it's increasing at a constant rate. And we can determine that constant rate that it's increasing at by finding our slope. So we'll do just that. Remember, we find our two nice points. Here's one, and here's another one. Now our slope, we can use rise over run because we have a graph. Now, of course, if you would like to use the equation, you can do that too. So my rise here is going to be 15, go up to 15, and then my run is 20. So my rise is 15 and my run is 20. So that will give me a slope or a rate of change of 3 over 4. And it doesn't matter where on the graph I measure this slope, it's a constant slope of 3 over 4. Now, if we look at the graph on the right, this does not form a perfectly straight line and therefore is non-linear. Now, I can't find the slope of this. It's not the same all the time. So the y values are increasing at a changing rate. They start by increasing at a slow rate, and then the rate at which they're increasing begins to get faster and it's increasing more rapidly. Now we can't find the slope because it's always changing. So because it's not consistent and it's not this perfect line, we cannot find our slope. Next, we're going to determine if a relation is linear or nonlinear from a table of values. So we want to continue looking at our equations, looking at our graphs, looking at our table of values and our concrete examples, and looking at all of those forms of our linear relations. Now, when we want to determine if a relation is linear from the table of values, we use what are called the first differences. And the first difference is a calculation in the change of y values as the x values increase at a constant rate. So I need to ensure that my x values are increasing at a constant rate, and then I want to check to see if my y values are also increasing at a constant rate. If they are, then I have this linear relation that I do on the left here. So let's calculate some first differences. So to do this, I want to find the differences between each of my values. So what I'm going to do is I'm going to take this value and subtract the one above it. So 10 minus 0 will give us negative 10. Oops, sorry. Not negative 10, just 10 minus 0 will give us 10. Then we're going to do that again. So we take this one, subtract this. 20 minus 10 equals 10. Then we do this one. 30 minus 20 equals 10. Now, if you notice here, the changes in my x's are consistent. So it's changing by 10 every single time. Now let's try the y's. So same thing. Take the second one, subtract the first one. 7.5 minus 0 will give us 7.5. Then 15 minus 7.5 will give us 7.5. And then 22.5 minus 15 will give us 7.5. So because they're consistent on both sides, that means this is linear. So we can say for linear relations, the first differences are the same. So we have 10s on one side, 7.5s on the other. Because all the x differences are the same, and because all the y differences are the same, this is linear. Now let's look at the one on the right. We're going to do the same thing and determine if our first differences are the same. So we have 4 minus 0 is 4. 8 minus 4 is 4. 12 minus 8 is 4. So off to a great start. Our x's are increasing consistently. Now let's look at our y's. So we have 1 minus 0, which is 1. 3 minus 1, which is 2. 7 minus 3, which is 4. So if you notice here, the changes in our y's are not the same. This means that this is nonlinear. And it's because the first differences are different. So it's very important that we check the first differences because it's very easy and quick to know if it's linear because they have to be the same. Let's try a few more examples. So let's look at this first one. We want to determine if it's linear. So to do that, we find our first differences. So 4 minus 2 is 2. 6 minus 4 is 2. 8 minus 6 is 2. 10 minus 8 is 2. 12 minus 10 is 2. So far, so good on the x's. Now let's look at the y's. 9 minus 6 is 3. 12 minus 9 is 3. 15 minus 12 is 3. 18 minus 15 is 3. And 21 minus 18 is 3. So therefore, this relation is linear because the first differences are the same. Okay, let's try another one. So for this one here, we want to determine if it's linear. We're going to do it the same way. So 4 minus 0 is 4. 6 minus 4 is 2. 8 minus 6 is 2. 12 minus 8 is 4. 14 minus 12 is 2. Okay, so we notice that our x's aren't the same. So we'll still check our y's because it's important that we check both. So let's check the y's. 2 minus 1 is 1. 3 minus 2 is 1. 4 minus 3 is 1. 5 minus 4 is 1. 6 minus 5 is 1. So if we look here, our y's are constant, but our x's are not. And that means that this is nonlinear. And that is because the first differences are not the same. Okay, now let's try this last one. This one is a little bit tricky, so bear with me. So the first thing we want to do is find our first differences. So 1 minus 0 is 1. 3 minus 1 is 2. 5 minus 3 is 2. 8 minus 5 is 3. Okay, so they're not the same on this side, but let's check the y's because maybe there's something else going on here. So we have 10 minus 5 is 5. 20 minus 10 is 10. 30 minus 20 is 10. 45 minus 30 is 15. Okay, so in a case in which my x's are all different and my y's are all different, I want to just double check one more thing. Sometimes I could just be missing some points in my table of values. So because both sides are not the same, so it's not like I have one side that's the same and the other's different, or they're both the same, I have to take a bit of a closer look. So if I notice on the x column, my first differences are 1, 2, 2, 3. For the y's, I have 5, 10, 10, 15. There's a pattern there, right? If I look here, 5 times 1 is 5. 5 times 2 is 10. 5 times 2 is 10. 5 times 3 is 15. So what this means is that I'm missing some of the points in between. So it is important that I double check if both my x's and y's are different. So this is linear because neither the x nor y column has the same first differences. However, they are related and we see a pattern on either side. So that's the only thing to look out for, is if they're both different, we just look for that pattern, and if it's there, it's linear. If it's not, nonlinear. Okay. The last piece here is determining whether or not a relation is linear from its equation. So what I want you to do is I want you to pause the video and I want you to look at these equations below and I want you to check them out on Desmos. So use this link just to see which ones are linear. So give them a try and pause the video right here, type them all into Desmos and see if they're linear. Once you're done, come back to the video and we'll go to the answers. So now that you're done, we want to determine if they're linear. So the first one, you should have had linear. The second one, nonlinear. Third one, nonlinear. Fourth one, nonlinear. Now here's the conclusion. A relation is linear if all variables have an exponent of 1 That's the first piece. And they all must be in the numerator. So we can't have any exponents on variables, and we cannot have any variables in the denominator. Now, it's nonlinear if a variable has an exponent. So some examples of nonlinear would be x cubed, y to the power 4, z squared, anything that has an exponent on a variable, or if we have a variable in the denominator. So for example, I have 2 over x, 3 over y, anything like that. Okay, so let's look at these ones below and find the ones that are linear. So remember, exponents only to the power of 1 on variables and no variables in denominators. So this one has to be linear. This one here has an x squared, so it will be nonlinear, and it's because x has an exponent. This one here, we need to make sure that we fully simplify it first, just to make sure we don't miss any exponents. So 2x multiplied by 4x will give us 8x squared. Because it's squared, this is nonlinear. Then the next one, although we have an x to the power of 1, we also have this x to the power of 2 hanging out, so it is nonlinear. Now for this one, just like we looked at before, x, y, I'm multiplying two variables together, so we should add that one up here. Two variables multiplied together. So just like we looked at in the other lesson, that gives us this shape. So it is non-linear. This one here, we have a variable in the denominator, so non-linear. This one here, we look, all of our variables have an exponent of 1, no variables in the denominator, no variables multiplied by each other, so that's linear. And this y equals 6, if you think back to our lessons from a while ago, this one's going to look like this at 6, so that would be linear. Now you can try the practice questions that are attached to the package that was printed out for you.